To infinity and beyond!
25 years ago, Toy Story was released, and while it's not my favorite Pixar movie, it's an extremely important one. Some might argue it's more important than, say, internal standards and the response factor, but we're going to focus on this for now. So, let's recap the internal standard method. Let's not read all of this problem right now, let's just read the first sentence. Let's say we have two chemicals, some analyte in blue that we're interested in, and some red internal standard. In this method, our standard is a completely different chemical from the analyte, but it still retains the definition of a standard in the sense that we know everything about it. We know its identity and concentration. And the standard is mixed in with the analyte solution that we're interested in, and we run both of them through whatever instrument we're using at the same time. In this case, our instrument is chromatography, and this is a common technique for use with chromatography and quantification analysis. Now let's say we run that mixture through some type of chromatography column, and we get the following chromatogram, where the signal for the blue analyte chemicals is about 4 times the size of the signal for the red standard chemicals. And in a chromatography analysis, the signal that we're ultimately measuring is the area of the peak. And so that brings us to this equation here, where we just set up a simple equality based on ratios. The ratio of area to concentration of one chemical, in principle, should be equal to the ratio of area to concentration of the other chemical. There is one monkey wrench that gets thrown into this, which we will address momentarily, but this is how it would ideally work. And so let's say that you knew your standard had a concentration of 3 micromolar, and the chromatogram tells us that the area of the analyte is 4 times the size of the area of that standard. Well, that means this concentration should be 4 times the concentration of the standard. In other words, 4 times 3, 12 micromolar. Again, there is one monkey wrench to take into account, which is this concept called the response factor, F. This term accounts for the fact that not all chemicals are detected equally by the detector here. And so now let's finish reading this word problem. The word problem tells us that our mixture of analyte and standard is actually in equal concentrations of both. They are not different by a factor of 4. But the problem also tells us that the detector has a response factor of 4. In other words, F equals 4. So what does this mean? Well, knowing that these two concentrations are equal, we can cancel them out and be left with just this equation. And what F is telling us is that in equal amounts, the detection of X is 4 times that of S. That agrees with the math in this equation. Think about it. We know that we have equal concentrations of our two species. However, the area of the blue species is 4 times larger than the area of the standard, despite the fact that they are present in equal concentrations. And so that agrees with this. If I plug in 4 for F, then this equation would be telling us that the area for the analyte should be equal to 4 times the area of the standard, provided that we have equal concentrations of the two. And the reason why this discrepancy exists is simply that the detector is able to measure the blue particles 4 times as often as the red particles. So let's just finish this with an animation. 4 blue particles go in, they all get detected. 4 red particles make it in. 1 gets detected, even though the other 3 are present. We just don't register them, and that's why this peak is 1/4 the size of this peak over here. So hopefully that all makes sense. Let's apply this to an example. And this example is as long and arduous as it's going to get. I would not put this full-length problem on a test, but any step in the problem is fair game. So let's just go through it. In a chromatography experiment, an unknown analyte X was ID'd as ethanol. However, its concentration remains unknown and must be determined. To determine the concentration, a methanol internal standard was used. To effectively use this, we first need to find the response factor. Only then can we find the unknown concentration. So this problem is going to be broken into 2 parts. First, we need to find the response factor. So to do this, we measure a known amount of internal standard and analyte. Remember, we know the identity of the analyte is ethanol at this point. It's just that its concentration is unknown in some sample of interest, but we're going to ignore that sample for the first part of this experiment. We need a sample where we know everything about both chemicals, the concentration of standard and analyte, so that we can figure out that F term in the equation. So let's say that we prep our mixture so that both concentrations after everything is mixed together are 0.550 molar. Having equal concentrations will make the math a bit easier. But we don't have to do it like this. This mixture is run through the chromatography column and we get the following chromatogram. The signal for the ethanol analyte is 523 and the signal for the standard methanol is 531. What do we do with this information? Well, it winds up being a pretty straightforward algebra problem, so here we go. Let's move that up and get some space. And let's write that we are dealing with the example from slides 3 through 5. And right now we are dealing with step 1. And we're just going to use that internal standard formula from earlier. I'll write it out again, but it's just the area of our analyte over the concentration of our analyte in the mixture, so final concentration, is equal to the response factor, which is what we're trying to solve for, times the area of the standard over the concentration of the standard, also in the mixture. I keep stressing the words in the mixture to emphasize the fact that these concentrations are not the initial concentrations when the standard and analyte were separate from one another. But once we mix the two together, they form a solution of larger volume, thereby diluting their concentrations to these final values, hence the F subscripts. This will be important in the next step of the problem. From here, we just plug in our information. It's an algebra problem. Area of the analyte is 523. We know the concentration of the analyte in this particular mixture because we made it, 0.550. We don't know F, again, that is our goal, is to figure that out. The area of the standard is also provided in the data, 531, and we know the standard's concentration was also 0.550. Technically, I didn't even need to write those concentrations. Since I knew they were equal, I knew they would cancel out. But it doesn't hurt to write, especially because... But it doesn't hurt to write them in anyways to be complete, especially since maybe the concentrations won't be equal in some problem I give you later, so we want to develop good habits of writing everything. From here, solve for F, and we get F is equal to 0.974. As I said when we first covered the response factor, it's important that you not only understand the math, but you also understand the meaning of F. So, in this case, what that number means is, given equal concentrations of X and S, the signal for X will be 97.4% as large as S. So let's write that. Given equal concentrations of X and S, given equal concentrations of X and S, the signal for X will be 97.4% as large as S. The signal for X will be 97.4% as large as 4S. Now that we have the response factor, we're ready to make proper comparisons between the internal standard and the analyte in our sample of interest. So now let's move on to that unknown solution. Again, this is a rather long problem. To determine the concentration of analyte in the actual sample, 10.0 milliliters of 1.00 molar standard were added to 10.0 milliliters of the unknown. And the concentration of these 10.0 milliliters is our goal. But we are actually going to run this 20 milliliter mixture that we get after we add the two together, therefore diluting both of these concentrations by a factor of 2. So we're going to learn what the new concentration of the unknown is and then back calculate what it was before using the good old dilution formula. So let's just do the problem. Step 2, and it starts just like step 1. It's with that internal standard formula. Not going to bother writing the symbols yet again because you already have that in your notes. I'm just going to start plugging in numbers. In this case, the chromatogram shows an area of 205 for our analyte. So 205 over the concentration of the analyte in the mixture is equal to F. Well, we know what F is. If we hadn't done step 1, we would have a second variable in this formula and there would be no way to solve it. But we learned that F is 0.974. And if we just pretended that number didn't exist, we would get the wrong answer for our concentration. So we really had to do that first half of the problem. So that number is going to multiply our other ratio. The signal for the standard is 483. And we know its concentration. It may have started at 1.00 molar, but now it's been diluted. And I'll quickly do this off to the side, but we should be very comfortable with M1V1 equals M2V2, right? So initial concentration, 1.00 molar. Initial volume, 10.0 milliliters, is equal to our second or final concentration of the standard times our second or final volume, which is just 20.0, and solve for SF, and we get 0.500, as is already indicated in the visual. Let's write that in, 0.500. And I'm not going to bother writing units, because we know whatever concentration unit goes in, that's what concentration unit I'm going to get out. Now it's just algebra. Solve the algebra correctly, and you should get a final concentration of the analyte being equal to 0.217 little 9. 217 little 9, and now I'll put the unit of molar. Why the little 9? Because we're not done with the problem. We don't care what the concentration of the unknown was in the mixture. We care about what it was before we did anything to it. And so once again, we need that dilution formula, but this time we're going backwards. What is the first molarity, or the initial concentration, of our analyte, times its initial volume, which we do know. It's also 10.0 milliliters. And we now know its final concentration was 0.217 little 9. And the final volume of that mixture that was run through the chromatography column was 20.0 milliliters. Then we just do the math and solve for initial concentration of the analyte, which is equal to 0.436 molar. 0.436 molar. And there you have it. So it is a long problem, but at the end of the day, it's pretty much all just algebra. The main difficulty is understanding the logic of all the steps and why we do them in the order that we do. If you get that, these problems aren't that bad.